In this video, we're going to talk a bit about the search for large prime numbers. And when I say large prime numbers, I mean astronomically large prime numbers. So to begin just with a little bit of history, in 300 BC, Euclid proved the most basic result about prime numbers. Euclid proved in 300 BC that there were infinitely many prime numbers. This means that no matter how large of a prime number you find, not only is there a prime number larger than that one, but continuing out that reasoning over and over again, in fact, no matter how large of a prime number there are always infinitely many primes past that number. Now, just because we know that there are infinitely many prime numbers does not mean that we know where they are and what those numbers are as they go farther and farther out. The largest known prime number is not this number. I do want to clarify that. The largest known prime number has this many digits. That's 24,862,048 digits. So imagine trying to write out that many digits. That's how large the largest known prime number is. And what's astonishing by Euclid's proof is that we know that there's infinitely many more even larger prime numbers out there, larger than this one. And I believe y'all will watch a nice quick video about the search for the largest prime numbers where you can actually get a visual on just how many digits that would be. Now, this largest prime number was found by this gentleman based on the Great Internet Mersin Primes search in 2018. Now, in the search for larger and larger prime numbers, the ability to factor large composite numbers, we know composite numbers are just numbers that are not prime, i.e. they have other factors other than one in themselves, into their prime components is of great importance to the study of cryptography. And to this point, there's no known formula that will consistently generate prime numbers. So there's no mathematical formula that we can type in values and then get a guaranteed prime number back as a result. So while there's no known formula that will consistently generate prime numbers, consistently as in every time you get the desired result of a prime number, there is some successful attempts so far to find a formula that can generate prime numbers. So one of the most successful attempts was by a French monk, Mersin. And because of that, we talk about Mersin numbers and Mersin primes. So the formula for Mersin numbers is for natural numbers 1, 2, 3, and notice the ... means it can continue on. We call these Mersin numbers, and specifically, you label it with the subscript of what natural number generated that Mersin number. So for instance, if I wrote m sub 2, that's the Mersin number where I plug the natural number 2 into the formula. And what is the formula? The formula is 2 to the n as an exponent minus 1. So the second Mersin number is 2 squared minus 1. And we see here the subscript for this natural number took the place of the exponent. Okay, calculating that, 2 squared is 4, minus 1 is 3. So the second Mersin number, m sub 2, is the value 3, which is a prime number. And we found that if n starts being a composite number, because remember natural numbers are either prime or composite, then the result will also be composite. So you're told if you start with composite, you'll end with composite. If you start with a natural number that's prime though, and you've evaluated it in this Mersin number formula, then m sub n, the Mersin number, may be prime or composite. So we know when it's composite, and then we have been told that if you evaluate this with a prime number, maybe it's prime, maybe it's not. The prime values of m sub n, so we find all the Mersin numbers, some of them are prime, these are called the Mersin primes. And it is interesting to note that large prime numbers that are currently being verified are typically Mersin primes. So this is one way that people, when they're searching for larger and larger prime numbers, do so by using the Mersin formula. In this case, we're going to be asked to use this formula, find the Mersin numbers, if we let n take on the value 2, calculate it again if we let n take on the value 3, calculate it again if we let n take on the value 4, and for each of these three tasks, we need to identify if the resulting Mersin number is prime or composite, and to do so we might want to reference our list of the primes less than 100, which I definitely recommend you have handy next to you during all of the homework and quizzes and lecture notes for this chapter. Let me just write down the formula again. The Mersin number formula is for natural number n. You would raise 2 to that natural number, and then once you calculate that result, subtract 1. So we're going to break this down into 3 calculations when n equals 3, when n equals 2, when n equals 3, and then when n equals 4. So the second Mersin number is 2 squared minus 1, because notice we are substituting the number 2 in here for the exponent for our m sub n. This is going to be called m sub 2 because it's using the natural number 2. And we already calculated this. 2 squared is 4 minus 1, so we get m sub 2 is 3. And thinking about our known prime numbers, we know that 3 is prime. Continuing this for n sub 3, using the formula, we know the third Mersin number, 2 cubed minus 1. Now, if you're typing this into your calculator, you could say 2 times 2 times 2, because remember, exponents are a repeated multiplication. Or if you prefer, you could use your exponent button. 2, the exponent button looks like this on most calculators, 3. And in either case, we would get that 2 cubed is 8. Subtract 1. And we would get 7. We know from our prime numbers less than 100, 7 is a prime number. And now I'd recommend that you take a moment and pause the video and calculate the fourth Mersin prime, or the fourth Mersin number. Identify if it's prime, unpause to check your work. We know the fourth Mersin number is 2 to the fourth minus 1. 2 to the fourth is 16. Subtracting 1 would give us 15. And we know 15 is a composite number because, for instance, its factors are 1, 3, 5, and 15. Definitely not prime. And this fits the rule we were expecting because it's not prime, which means it's composite. And we could have expected that from this description because it said if you start with a natural number that's composite, which 4 is composite, then if you plug that into the Mersin number formula, the result will also be composite. Okay. Now, there's a bit more historical detail that we could get into that I'm not going to talk about in this video, but if this has piqued your interest at all, I recommend you go to page 187 of our textbook, and it describes some interesting history about the Mersin Primes over the centuries. Particularly of interest, I think, is what was discovered before the advent of computers, because we could imagine that computers would really help with some of these very large calculations. For instance, 2 to the fourth was already 16, 2 to the fifth is 32, and then it just keeps building upon that, and that's even relatively small Mersin numbers. So with the aid of computers, the largest Mersin prime ever found was this one, the Mersin number here. But before the invention of computers, Pierre de Fermat, who lived during this time period, was a hugely influential mathematician, and many of his results and hypotheses are still being used and attempted to be proven today. Fermat, at his time, conjectured that this formula, notice the F for Fermat, subscript n, that's any natural number. If you raise 2 to the exponent 2 to the n, so this is an exponent nested within an exponent. And then if you add 1, he conjectured that it would always produce a prime number. And in fact, if you check the first 5 Fermat numbers based on this formula, so f sub 1, f sub 2, f sub 3, f sub 4, and f sub 5, checking those 5 first, you do get all prime numbers. Okay. And I do apologize with this. I should have started at f sub 0, since the formula does work with any whole number, and 0 is a whole number, so these are our first 5 Fermat primes. But the 6th Fermat number, f sub 5, is this digit, which definitely you can't tell just by looking at it, but people have calculated that this is actually not a prime number. And one thing to note, if we actually calculated the fourth Fermat number, the fifth one, f sub 4, you would get 65,537. And at the time of Fermat, back in the 1600s, he identified this was a prime number, which I think is just astonishing that only with the aid of his mind, concentration, and patience, he was able to identify or conjecture that this is a prime number. Where today, we would kind of balk at the challenge without being able to use a computer to go through those calculations. And as of 2014, no more Fermat primes have currently been found. So let's just practice by calculating one of the Fermat numbers. Let's find f sub 2. Now we know the formula is 2 to the 2 to the n, so the exponent is whatever subscript we're talking about here. So this 2 is going to take the place of the n in this formula. So we're going to write it out in general first, 2 to the 2 to the 2. And then we add 1. I recommend that you calculate the first exponent first in your calculator. 2 squared is 4, so I could rewrite that as 2 to the 4th plus 1. And now we need to calculate this. Now 2 to the 4th, either just by multiplying it in your mind or typing this into your calculator, you would get that that is 16. So this simplifies to 16 plus 1, which is the number 17, which we know is a prime number. Now from this section, you're not asked to do any homework from the textbook. It's not in the textbook, but it is written here in the notes. So 5.2 homework, you need to answer these questions. Notice you're asked to calculate the 5th Mersin number, the 6th Mersin number, calculate f sub 3, f sub 5 based on these formulas that we just talked about. And all of the solutions for each of these will be in Canvas, and it will be included under the blank notes for this. So look for just 5.2 homework solutions. So I recommend you do all these first and then check your work. And from the 5.2 section, if you're comfortable doing any of these 5 problems and very confident in it, then you'll definitely be prepared for anything that you see in the 5.2 quiz.